Okay, here we have a solids of revolution problem, and we're going to use washers in this example. Specifically, we want to find the volume if the region bounded by the line y equals x and the parabola y equals 1/3 x squared is revolved about the y-axis. And we want to find the volume of the resulting solid. So I want to sketch this first. And here I have the line in red and the parabola in blue, and we're revolving this about the y-axis. So I have this object here, and you might notice that we have this inner cone here and an outer paraboloid. And we want to find the volume of this, so we're going to use cross sections. So for my first one, I might take 4 of these, like so, and that's going to give me an approximation for the volume. And we get a better approximation if we take more. So here I'm taking 18 washers, and this will give us an approximation there. So we can look at this from a little bit below here, again to get a feeling for this object. And then if I take a vertical cross section, I can see what's going on with my washers, right? And again, we have the outer paraboloid and the inner cone. So we want to find the volume of this ith washer. So here I have this illustrated. I have an inner radius, an outer radius, a thickness is change in y, my paraboloid. And the volume of this object, this washer, is a cross-sectional area, which you can see is the area of this region in light blue, times the thickness, which is the change in y. So I have this pi capital R sub I squared is the area of the outer circle minus the inner circle's area, which is pi little r sub I squared, and the thickness is the change in y. So my parabola, is this y sub I is 1/3 x sub I squared. But I can write this as x in terms of y. And this is exactly what we want to do because our x sub I here corresponds to our outer radius r sub I here. So because we have a thickness change in y, I want this radius here, this capital R sub I, in terms of y. So our capital R sub I here, we have square root of 3 y sub I. Next, we want the inner radius. And for the inner radius, we're on the line y equals x. So we just have our little r sub I is y sub I. And for my volume here then, I have the cross-sectional area times the thickness. I can rewrite this all in terms of change in y and y sub I. And then we can simplify this a little bit. So this is going to be the volume of this ith washer. So if we sum up the first n washers, we get an approximation for the actual volume. So here in my illustration, n was 18. And we can write this in sigma notation as the sum I equals 1 to n of this 3 pi y sub I minus pi y sub I squared change in y. And then what we do is we let n go to infinity, and our change in y is going to 0. And we have the limit of Riemann sums gives us this definite integral. Here y is going from 0 to 3. If you look at the original graph, you can see that that's where our y values are going from. Notice that there's no longer the I subscript in here anymore, and the change in y is going to correspond to the dy here in this integral. So we use a fundamental theorem of calculus in the power rule. So that when we integrate the y here, we have our 3/2 y squared, and to integrate the y squared, we have 1/3 y cubed. And then we just put the numbers in there. We put 3 in place of y, minus when we put 0 in place of y. We do a little subtraction, and finally we get the volume is 9/2 pi cubic units. Thank you.